Morning, Danny. Morning, Danny. I'll always go live a minute before class starts, and then I'll start class a minute after. So I'll come live at 8:39, and then I'll start teaching at 8:41. Morning, Chandler. All right, here we go. Okay, so first thing we'll do is go over homework. Any questions on the homework? Page 206, 6.1, 1 through 6 all. Questions? Nothing? Okay, I'm going to call out the answers. Make sure you check your work. All right, number one, I remember that has an A through an F. Number 1A is no. 1B is yes. 1C is yes. 1D is no. 1E is yes. And 1F is no. Number two, 2A is no. 2B is yes. 2C is yes. 2D is yes. 2E is no. 2F is no. Number three, 3A is no. 3B is no. 3C is yes. 3D is yes. Number four, 4A is yes. 4B is yes. 4C is no. And 4D is no. All right, so 5 said find the values for J, K, L, and M. J is 2, K is 1, L is 4, and M is 3. All right, and then the last one you had proof, and then they gave you the statements. They just needed to come up with the reasons. So let's see, this is 6, and it's going to go 1, 2, 3, 4, 5. 1 is given. 2 is corresponding parts of CP/CTC. Number 3 is a segment addition postulate. 4 is a property, one of those properties of inequalities, and 5 is substitution. And that was it. All right, make sure you have your homework turned in. I'll probably, starting tomorrow, if you turn them in late, I'll start putting in zeros. But for that first homework assignment, I'm going to give everyone about 2 days to get it turned in. But like I said, starting tomorrow, I'll probably put in zeros when you fail to turn in your homework. So make sure it gets turned in. If you're running into any technical problems, taking pictures or whatever, just send me an email, let me help you out, or send me a chat. You guys are pretty good at sending chats yesterday. Just remember, if you send me a chat, I got to teach at the same time, so I probably can't answer too many chats unless I finish a class early. My first break comes around 12:30-ish, and that's when I can start answering emails and chats. All right, we're moving on. Let's see, quiz on Friday. We'll talk about it Thursday tomorrow. We're doing section 6.2 today. Here is your homework. Now, as always, remember, this is, you can certainly copy it down, but remember, when you click on Teams, this information appears right there, and it will go live at 7 a.m. every morning. You can look at this. I already got Amaya's already done her homework, so good job, Amaya. This is one of the more challenging classes too, so if you figured it out all by yourself, good for you. All right, For the rest of us, we're moving on. Okay, this is a challenging class. So it's two brand new concepts, something called inverses and contrapositives. In the big scheme of things, I'm going to give you a pattern to follow. You're going to follow the pattern. It's not going to be that big of a deal. But if you don't pay much attention to this, boy, is this some challenging. You're not going to pull out either one of these words just by looking at them, trying to figure it out. All right, so the last class we talked about inequalities. In fact, this chapter deals with inequalities. Today doesn't deal with inequalities. Today we go off on a little tangent, so to speak, and we talk about two other logical constructions, something called an inverse and something called a contrapositive. Okay, so this chapter is about primarily about inequalities in geometry, but today we're going to be talking about these two other logical constructs. We've already dealt with two of them. We've dealt with conditional statements, and we've dealt with the converses. But what we haven't, there's more. What we haven't dealt with is inverses and contrapositives. So the two that we've seen already were your standard statement, if-then statement, and then we've constructed a converse to that. And we've had many theorems that were converses to other ones. So you really, really, really got to pay attention. This is not a class that I would give to anyone but a high school student or higher. This is some challenging material, so please pay attention. Here we go. Way back in chapter 2, we talked about conditional statements. These were your if-then statements. So, and this is the one that I used way back in chapter 2, if you remember. And it was, if it is raining, then the sidewalk is wet. Okay, so if it is raining, then the sidewalk is wet. My phone's going off here. This is called an if-then statement. Why is it called an if-then? Because it literally has the word if, comma, then. We call this in mathematical speak, we call this a conditional statement. That if you meet the first condition, then the following condition must occur. So this is called an if-then statement, and we have a shortcut method of writing this. If you remember right, it's if P then Q. The only reason we have this if P then Q is just for a general notation of a conditional statement. So I wish they would use letters different than P and Q, because P and Q look alike to each other, but that's what they use. So if P then Q is what's called a conditional statement. We've seen this many examples before. So the first thing I want you to write down is, this is something you've already written down a time or two before, but I want you to write it down one more time, just so that we have it next to what we're going to do today. So the first one is we're going to talk about or remind you of is the converse. So if a conditional statement is if P then Q, a converse flips those completely around. So instead of it being if P then Q, a converse statement takes the P and the Q and just simply flips them around. So we say if Q then P. So in this particular, and that's the part I want you to write down. So in this particular statement, look at our if then statement. From the conditional, we have the P is it is raining, and the Q would be then the sidewalk is wet. So if it is raining, then the sidewalk is wet. If we flip those around and construct the converse, all we do is we flip around, and I've made it color-coded, the blue and the red. So it would say, if blue, then red. You see the colors? So if I were to construct the converse of the statement, if it is raining, then the sidewalk is wet, the converse would be, if the sidewalk is wet, then it's raining. And we've seen this before. We've had many theorems that were converses, and we will continue to see that. Well, it turns out there's two more constructions like this. One's called an inverse and one's called a converse, and that's primarily what this class is on, inverses and contrapositives. I said converse, I meant contrapositive. So two foreign words to you that we're going to have to define. All right, so we good on this slide? Okay, moving on. So stay with me. This can get a little bit messy. The understanding will come after practice. Typically, you're not going to understand the difference between converse, inverse, and contrapositive immediately. But if you have it in your notes, in your book of truth, you will be good to go. So here comes the first new one. All right. So this is going to be called an inverse. So in the big yellow box there is what you're going to write down. So we're going to create what's called an inverse to this statement, if it is raining, then the sidewalk is wet. And remember, we're going to call this if P, then Q. So the inverse, this is what goes in your book of truth. So in the inverse is if not P, then not Q. If not P, in other words, you're going to negate or make P false, then you're going to make Q a false statement. How do you make them a false statement? You literally typically put the word not there. Not. If you are, I am 16 is a statement. If you want to negate that, then you would say, I am not 16. Okay, so how does that work with our statement? If it is raining, then the sidewalk is wet. Well, notice the P and the Q on the inverse do not flip-flop. It still stays exactly the same. You're just going to negate both statements. Well, how do you negate it? Well, typically you put the word not. So it says, if it is raining, so now we're going to say, if it is not raining, then the sidewalk is not wet. So that's how you construct an inverse. So inverses are not hard to construct. What is generally hard to remember is, well, what's the construct? So if you have this in your notes, if not P, then not Q, and this perfect example right here, I mean, I would put everything that's on this slide in your notes, and then it's easy to construct an inverse. You just follow this construction as it appears on the screen. So if we're given the initial if-then statement or the conditional, if it is raining, then the sidewalk is wet, that is an if P, then Q statement, and you're asked to create the inverse, then you negate the first phrase and you negate the second phrase. In other words, you negate P and you negate Q. So if it is not raining, then the sidewalk is not wet, is the inverse. Questions? I forget, is that Wes? Is M?
Yeah, that's me.
Okay, cool. All right. I'm going to pause here. I want to make sure this is in your book of truth. Tonight for homework, you're going to be asked to create an inverse of a statement. If you don't have this written down, you're not going to remember it. Clearly, a year from now, you're going to remember doing inverses, but you probably won't remember it either unless you commit it to memory. It's one of those things that you got to have a notation for it to remember it. We good to go? Can I move on? I hear no one saying no, so I'm moving on. Okay, so there's only one more today, and it's called a contrapositive. So it's the same idea. I'm gonna, here's our original statement, our conditional. If it's raining, then the sidewalk is wet. Here is what's called the contrapositive. So the contrapositive flips the P and the Q around. So if Q, then P, and negates both of them. So it's kind of like a combination of the converse and the inverse. And we call it the contrapositive. So if not Q, then not P. If not Q, then not P. Hard one to remember. And let's see if I can make this construction. So I got to take Q's got to be my first part, and I got to negate it. So initially it says the sidewalk is wet. So I'm going to say if the sidewalk is not wet, and now it says do not P, so I'm going to negate P. If the sidewalk is not wet, then it is not raining. So there would be your conditional statement created as a contrapositive. If the sidewalk is not wet, then it is not raining.
The only thing you can do to the top one is pull out an X.
And I'm going to pause here, make sure you guys have this copied down. Once again, I would, if you're on a page, you could have one page that said converse, inverse, contrapositive. You'd have that first statement there. If it is raining, then the sidewalk is wet. If P, then Q. And then for the inverse, you would have, for the converse, you'd have if Q, then P. For the inverse, if not P, then not Q. And then for the contrapositive, you flip-flop the P and the Q. If not Q, then not P. Okay. Tell me if you need any more time. Anybody? All right, tonight for homework, they're going to give you a conditional statement, ask you to create a converse, an inverse, and a contrapositive. All right, so what is all this about, and why do we have these four things now? Well, it turns out that we have some consequences to these four: the conditional, the converse, the inverse, and the contrapositive. So basically, I'm going to show you this slide, and then I'll allow you to copy down the notes. So if your original conditional statement is true, and remember, the only conditional statements we have in geometry are true ones, but that's not true in life, right? But if you are given a true conditional statement, if it is raining and the sidewalk is wet, right, we would accept that to be a true statement. If it is true, the converse might be true. The converse does not always have to be true. And it turns out that the inverse also might be. Don't panic, I'm going to give you examples of this. It turns out that the inverse might be true. Sometimes it's true, sometimes it's not. But here's the kicker. It turns out that if you're given a if-then statement that is true, then the contrapositive will always be true. And this is the hard one to remember, is that the converse and the inverse might be true, but the contrapositive is always true. So this is easier explained with an example, but I do want you to write this down next to all that stuff you just wrote. Put this as your next thing. And what we basically say is, if the if-then statement is true, if it is true, the converse might be true, the inverse might be true, but the contrapositive will always be true. And that's kind of a remarkable result. And I'll show it to you here in a second. So if the conditional is true, the converse might be true, the inverse might be true, but the contrapositive will always be true. Good to go? We have it all copied down? Also remember, this will be posted by 4 p.m. to class. The video of this, I will attach it to lesson 6.2 on Teams. So if you need to go back and rewatch the video, just remember it won't be done until about at least until 4 p.m. every day. Okay. One last thing, just remember, if the contrapositive is always true, that's dependent upon the if-then statement being true. Now, I can make an if-then statement be false, right? If the sun is out, then I will go to sleep. That may or may not be true. So we're talking about statements that are true. So this slide right here is when the if-then statement is true, or when the conditional is true, then the contrapositive will always be true, but it is dependent upon that the if-then statement is true. If the if-then statement is not true, then the contrapositive may or may not be true. But in geometry, our conditional statement is always true. So our contrapositive statement in geometry will also always be true. Converse might be true, the inverse might be true, but the contrapositive is always true if the if-then statement is true. So we better see some examples. So I'm giving you geometric examples right here. So watch me do the magic here. So if two lines intersect, then they are coplanar. In other words, if two lines intersect, then they intersect on one plane. Okay, and then that's a true statement. So that in geometry, and we've had that from chapter 1. Remember, if you have a flat plane, or if you have a plane and you draw two lines on it, the lines are either parallel or they are, if they're on one plane, they're either parallel or they intersect. Okay, so if two lines intersect, then yes, they intersect on one plane, so they are coplanar. If we were asked, and that's a true statement, if we were asked to construct the converse to that, remember the converse is if Q then P. So if Q then P, so let's see, if Q then P. So if two lines are coplanar, then they intersect. Well, let's see if that statement is true. Remember, the converse may or may not be true. So if two lines are coplanar, then they intersect. Well, that's true if they intersect, but remember, two lines on a plane could also be parallel, so that's not always true. So here's an example of where the converse is not true or not always true, even though that the initial conditional was true. So you got to kind of logically think this out. Tonight for homework, they're going to give you statements. They're going to ask you to create the converse, the inverse, and the contrapositive, and you got to figure out if each one is true or false. Okay. The inverse, let's see. Remember, the inverse is we take the initial conditional, if P then Q, and we negate both sides. So if not P, then not Q. If not P, then not Q. So let's negate both of those. If two lines do not intersect, then they are not coplanar. So if two lines do not intersect, then they are not coplanar. Well, that's not always true either, because the lines could be parallel. Now, that lines could be skew, right? That would make it true, but the lines could also be parallel, and therefore they would be coplanar. So this one is not always true as well, too. Now, you got to be careful. I remember the first time that I got this logic class, I thought it was always that this was the answer, not always true or not always true. The converse or the inverse could be true and they could be false. If the original conditional is true, sometimes the converse is true, sometimes it's false. So the answer to this one is, well, it's not always true. It's not always true for the inverse as well, too. However, here's the kicker. If you're asked to create the contrapositive, you don't even need to, well, if they ask you to write the contrapositive, please write it. But the answer to the contrapositive will always be true. I don't even need to construct it. Okay, you are absolutely guaranteed that if the conditional is true, that the contrapositive will always be true. So, well, let's see what that would look, because remember, I promised you an example. So remember, the contrapositive construction is you take the P and the Q, you flip them, and you negate both of them. So if not Q, then not P. So if two lines are not coplanar, then they do not intersect. Okay. If two lines are not coplanar, that means they don't live on the same plane. That means they're skew. The only two lines that don't intersect or don't exist on the same plane are skew lines, and skew lines do not intersect. So that one is true. But like I said, the fact that it was true, we didn't even need to write the contrapositive. If the initial statement is true, right? If the initial conditional is true, then the contrapositive is always true. You'll find out that this is helpful later on. Okay, one more time, one other example. So here it is in table form. So if P then Q, let's see what our statement is. If two angles are congruent, then they have the same measure. Well, yeah, that's a true statement. So here's the kicker. If the if then statement is true, immediately you can not assume, but you're guaranteed that the contrapositive is true. Even before I create it, I know the contrapositive is true. If the initial statement is false, then I don't know if the contrapositive is true or false. I need to write it and think about it. But if you're simply just asked, if you're given a true statement, is the contrapositive true? The answer is yes. The converse or the inverse, well, we need to create them to figure out if they're true or false. So let's create them. Let's see, converse, we flip-flop the P and the Q. So if two angles have the same measure, then they are congruent. So that would be just flip-flopping the P and the Q. If two angles have the same measure, then they are congruent. Well, that's true. So here's an example of where a converse is true. And remember, converses can be true or false. Okay? Inverses can be true or false. Contrapositives are always true if the initial conditional is true. Okay, so let's see. To create an inverse, we leave P and Q and we just negate them both. So if not P, then not Q. So if two angles are not congruent, then they don't have the same measure. Okay, and that's clearly true. So here's an example where every single thing is true. And like I said, if I want to create the contrapositive, I flip the P and the Q and I negate both of them. So let's see, if two angles do not have the same measure, then they are not congruent, and that we were guaranteed it to be true. So here are two examples. And what you can do tonight for homework, if you're struggling with these constructions of the converse, the inverse, and the contrapositive, wait till I upload the class, play this part of the video again, watch how I created them, and I think it'll be a little bit easier. Any questions so far? Geometry can be challenging. Today's a challenging day. All right, so here's one more dear to our hearts. I made this back before I thought that we would be e-learning. All right, this is what homework will look like. It will say, write the converse, the inverse, and the contrapositive, and then state whether each statement is true or false. So here's our conditional, and they're only going to give you true conditionals. Since we are in D49, if there's a blizzard going on, we will absolutely 100% have a snow day. That's a true statement. Okay. So let's see. Let's create the converse. The converse takes the P and the Q and flip-flops them around. So if Q, then P. So if D49 has a snow day, then there is a blizzard. Do we always have snow days when or if we're having a snow day, are we guaranteed that there's a blizzard going around? Well, the answer is no, because we've had snow days when the sun is out. We've had snow days when it's really, really, really cold out. We've had snow days when there's too much snow on the ground, but it's not currently snowing. So just because we have a snow day doesn't mean there is a blizzard. We've certainly had snow days when there's light snow falling as well too. Okay, when the roads are very icy. So the converse to this particular one is false. Now remember, the converse could be true or false. You have to determine. How do you determine it? Determine it, you write the statement out. Questions on that? All right, let's make the inverse. So the inverse is it takes the initial construction, if P then Q, and just negates both of them. So we would say if not P, then not Q. So let's negate the first one, if there is a blizzard. So if there is not a blizzard, then D49 will not have a snow day. If there's not a blizzard, we're not going to have a snow day. Well, that's clearly false as well too. Once again, we have plenty of snow days when there's not a blizzard. Okay, so that one's false. I'm going to say it for the 14th time. The converse and the inverse could be true, they could be false. You got to write that sucker out and figure it out logically whether it's true or false. The last one, I don't even need to write it out. I already know that it's true. If you're given a true statement, then the contrapositive is always true. But if it asks you to write the contrapositive, you got to write it. So let's see. How do you make a contrapositive? We flip-flop the P and the Q. So if Q, then P, and then we negate both of them. So if not Q, not P. All right, so let's see. Flip-flop. So, and then I got to negate. So D49 will not have a snow day if there's not a blizzard. Like I already could put true. I know this is true. So if there's not a blizzard, or if it's not a snow day, then there's not a blizzard, guaranteed. So if there's a blizzard, we know that there's going to be a snow day. So if there's not a snow day, right, if we're at school, we know that there's not a blizzard going on. Okay, so that seems relatively simple to construct. The issue is reading it and logically figuring out if things are true or false. But the cool thing is that if you start off with a true conditional, you don't need to do any thinking about the contrapositive. You just simply need to write it and just write true. Any questions on that? I usually see kids struggle not at the construction, but whether things are true or false. So generally it's the converse and the inverse that people struggle at, whether it's true or false. You just got to do close reading and figure it out. All right. Yeah, this is a little bit of sarcasm, right? So that was fun. So what? Well, the so what is that we can use this. I need you to write this down somewhere in your book of truth. So because we know that if a conditional is true, that the contrapositive is true, we now have two ways of proving a statement true. In other words, we have two ways of proving a theorem or a corollary. And that is we either prove the initial conditional or we prove the contrapositive true. In geometry, there will be times, not today, there will be times when it's really, really, really challenging to prove something. Now you have a second option. We can prove the contrapositive true. And if we prove the contrapositive true, then the initial conditional has to be true as well. Okay? And that's where this gives us an extra, tool in our tool belt in order to prove things. Okay? All right, so to prove a conditional statement, you prove either the statement, if P then Q, or you prove the contrapositive, if not Q then not P. Sorry. Everybody have that copy down? I wish if I had written the book, we would immediately use this skill to prove something. This book doesn't choose to do that. We will do contrapositives later on and throughout the book, but I really wish they would do one, but they don't. All right. The second new idea is there's going to be a new way of thinking about things logically. And some of you have seen this before, others of you have not. These are going to be called Venn diagrams. You may have heard of this. You may have even seen them before. Lots of other areas of study, history, English, they like to use Venn diagrams. These were invented literally by a guy named John Venn. That's why they're called Venn diagrams. He was a British mathematician, philosopher, He lived in the late to early 20th century. Did I say late 18th century to the early 20th century? Okay, this is what he looked like. All right, so you've seen this. You have these circles and you have statements inside the circle. So everyone who likes math, get inside that circle. Everyone who likes Oreos, get inside this circle, and I live right there because I like math and I do like Oreos. This is what a Venn diagram looks like. Okay, so we're gonna write down a few notes. They're gonna ask you to construct a few basic Venn diagrams. This is called what's called in mathematics called set theory. Set is a collection of objects. The circles represent a collection of objects. Usually when non-mathematicians make Venn diagrams, they forget that you're supposed to start with a rectangle, and it's called the big rectangle, and the big rectangle represents everything. And we call everything the universal set. The universal set includes everything. It's dogs, cats, bells, whistles, cars, trucks, people, everything. So the rectangle, and sometimes you will literally see a U on the rectangle. The U stands for universal set. People that don't know anything about Venn diagrams forget to put a rectangle. We will not forget. The sets of things that you talk about, hey, the people that like math, the people like Oreos, are represented by circles. And those circles, everyone who meets that criteria sits inside that circle. Okay, so those are the basics for Venn diagrams. And we're gonna just make a few. I forget how many you have tonight for homework. We good to go? All right, so how do you make a Venn diagram? I'm gonna leave this, we're gonna do, I think, 3 examples here. I will leave the steps up on every single one. So if you don't copy it down while we're doing it, you'll have plenty of opportunity. And remember, the video will be up by 4 p.m. So step number 1 is you draw a rectangle. Step number 2 is you draw a circle for each subset. The subset will be the statements. And you place the circle appropriately. That's kind of a big step right there, is you gotta put the circle where it needs to go. And you figure where the circle needs to go out by using basic logic. So I'm going to give you an example. Hey, there's only 2 steps here. Pretty simple, right? The universal set are going to be people. So inside my rectangle, I got to draw this. I forgot that I didn't have this on drawn, so I got to draw it. Okay, so we're going to make a rectangle. Mine is going to be horrible. All right, so there's my horrible drawn rectangle, and we'll put U right here in the upper corner, representing universal set. So my universal set is equal to people. People. P-E-O. I'm doing this with a mouse, cut me some slack. People. All right, so everything, all the people that ever existed or do exist are inside this rectangle. Let's see, next thing is a subset, people who like beef. All right, who likes, well, I would be in this circle. So this circle right here is going to represent, nice, horrible circle, great. It's going to represent people who like beef, right? Because remember, the only thing inside the rectangle are people. There's no dogs, there's no cats, no dogs like beef, cats like beef, but there's no dogs or cat inside our universal set because we limited it to people. Okay, so there's the circle, everyone, because not everyone likes beef, right? Some people are vegetarians, some people just don't prefer the taste of beef. I don't know, those people are strange to me, but they would be in here. All right, second subset will be people who like vegetables. Now, there are plenty of people who like beef and vegetables, so these 2 circles would overlap, and the overlap, I'm just gonna put veg, the overlapping of the 2 circles will represent the people who like beef and vegetables, and I would be a little dot right there. There's me. I don't know where you are. Wes, where would you be?
Same place as you.
All right, we got a dot there. Chris, where would you be?
Smack dab in the middle of beef.
Oh, sorry. So Chris doesn't like vegetables. And I mean, I don't want to make this seem like it's too complicated, but that's how you do Venn diagrams. You don't typically label all of the dots. You can. All right, questions on making a Venn diagram? Okay, I'm going to clear this out, and we're going to do one more. All right, so here are the instructions once again. So let's see. We start off with a rectangle. The rectangle represents the universal set. That's a little bit better. And we're putting polygons this time. So U equals poly. Now, this is how correct people make a Venn diagram. And like I said, typically people leave off the rectangle. So you don't even know what you're talking about. We need a subset of parallelograms. So here's our parallelograms, P for parallelograms. Then we got polygons with right angles. So let's see, that would be over here, polygons with right angles. So I'm gonna put RT angles. Okay, polygons with right angles. Well, lots of pentagon can have a right angle, but a parallelogram with a right angle is called a rectangle. So rectangle will be right here, smack dab in the middle. Okay. However, when we add our third, polygons with congruent sides, so we got plenty of polygons with, I don't have enough space, I'll just put congruency symbol. Polygons with congruent sides, hexagon can have congruent sides, right? Some hexagons have right angles, so they would be right here. No hexagons are parallelograms, so actually I need to erase my circle right here and make it slightly different, because no, so I need to be right here, a little bit of this, like that, okay? So I can have some polygons with congruent sides that also have right angles. I read this wrong. I had it right the first time. Let me undo that. I read that as polygons with congruent sides. And some of those are parallelograms. Oh, yeah, I had it right the first time. So a polygon with congruent sides could have right angles. A polygon with congruent sides could be a parallelogram, right? Those would be your a rhombus, or that could also be a square. And oh, by the way, squares have all three. So a square would be smack dab in the middle right here. So a square would be a polygon with congruent sides. It would be a polygon with a right angle, and it would be a parallelogram. So squares would live right smack dab in there in the middle. And this is kind of what they're going to have you do tonight. They won't be as complicated as this one. This is as complicated as it gets. Questions on what I just did? Venn diagrams are kind of fun. I don't know, or maybe it's just me. All right. It turns out that we can use Venn diagrams to prove things. It seems kind of strange, but it ends up being true. I'll give you an example. Let's see, all runners are athletes. All runners are athletes. Notice it never defines the universal set. So we could make the universal set as being people. And by the way, all runners, I think we can consider to be athletes. Or I'm gonna make that bold statement. That's a true statement. Okay, so my universal set would be people. We're not going to include dogs, even though some dogs are runners and athletes. Okay, so if my universal set is people, I need what? 2 circles. I need a circle for runners, and I need something for athletes. Well, if we consider athletes as containing lots of things, I mean, divers are athletes, but they're not runners. However, we know that all runners, right, because it says so, all runners are athletes. So therefore, the runners would exist inside the circle of athletes, right? No runner is outside that is not an athlete, because it tells us, it says all runners are athletes. Everybody buying that? Okay, so they're going to give you something like this, or ask you to construct this, and then they will ask you some questions. So for instance, it will say Leroy is a runner, and they will ask you to, I don't know, put Leroy in your Venn diagram. Chandler, where are we going to put Leroy?
In the runner circle.
Yeah, so Leroy, right? Leroy exists right there. So here's the deal, though. Leroy is a runner. That makes him an athlete, and that makes him a person as well, too. Okay, so what can you conclude? That Leroy is both a athlete, a runner, an athlete, and a person. Okay, seems kind of silly, but that's what they want you to do. Another question, same Venn diagram. Lucia is not an athlete. So where would, who do we have here today? Chris is here. Everyone else dropped out. Danny, where would Lucia live in my Venn diagram?
She's in the middle, right?
It says she is not an athlete.
Okay, then she's in the runners group.
But all runners are athletes.
What if she's just people?
Okay, she's just a person. So where does she exist? She exists outside the circle. She's a person, but she's not an athlete. Because remember, all runners, it says so, all runners are not athletes. This is where it becomes, okay, maybe a little bit tricky. You just got to be careful.
Okay.
Everybody get this?
Yep.
Okay. Linda is an athlete. So Chandler, where does Linda go?
In the athlete circle, but not the runners.
Well, how do you know that Linda isn't a runner?
Because it doesn't say.
Right? So can we conclude that she's not a runner from the statement?
No.
We can't. So here's the thing about Venn diagrams, is sometimes Venn diagrams won't tell you the complete story. So from this one statement alone that Linda is an athlete, right, what we can conclude, we can't conclude, it's basically the converse to the statement. It says Linda is an athlete, right? So we don't know whether or not, and this is why the converse is sometimes true and the converse is sometimes false. So if we were to flip that around, that Linda is an athlete, well, that she could be a runner, she might not be. So just because you meet the Q portion doesn't mean you meet the P portion. So this would be an example of a converse. Linda is an athlete. We can't conclude anything other than she's an athlete. So she could either live inside the runner circle or inside the athlete circle. We just don't know. Larry is not a runner. Larry is not a runner. What can we conclude about Larry? Anybody?
That he's not in the athlete circle.
If he's not a runner, well, he could be not an athlete, or he could live outside here. But just because you're not a runner doesn't mean you're not an athlete. This will be a case of the inverse. If not P, if you're not a runner, are you not an athlete? Can we conclude that? And the answer is, I don't know, right? If you just tell me he's not a runner, he could be, give me an athlete that's not a runner. You could be a football player. We don't say football players are runners, right? So therefore, you could still be an athlete. You don't know where Larry lives. Larry either lives inside the athlete circle or outside of the athlete circle. He certainly doesn't live inside the runner circle, though. So here's an example of, again, where the inverse may or may not be true, okay? All right, you kind of seen how this can be slightly more challenging than when it first appeared. Right? Usually the first Venn diagram they show you is a nice easy one, and then they flick on the heat here and make it way more challenging. Okay, most people at this point, you know, they're kind of thinking Venn diagrams are not as much fun as I thought they would be. They're kind of like this girl. All right, classroom exercises. Here's an example. It says classify each conditional as true or false, and then state if the inverse, contrapositive, or the inverse and the contrapositive. In other words, write the inverse and contrapositive and then state each is true or false. So here's the kicker. If the conditional is true, the contrapositive is always true. If the conditional is false, then you got work to do for both the inverse and the contrapositive. If the conditional is true, the inverse could be true, right? So be careful with that tonight for homework. And that was kind of it. Any questions on today's lesson?
No.
Cool. Then I will stop for today. Remember, if you ask me a question, I'm going to be teaching up until around noon, and then all the way up until 2:40. So I can answer the questions after those time frames. If not, no questions. We'll call it a day, and I will see you guys. To make sure you're taking pictures of your homework and attached it to the team's assignment. I'll see you guys tomorrow.